Hello everyone, welcome to IIT-JAM in Chemistry tutorial number 7 and lecture number 3 of Atomic and Molecular Structure chapter. Here we are going to discuss the Bohr theory will be continued, and in this context we are going to discuss energy of an electron, energy of transition of an electron, then hydrogen spectra, and finally the limitations of the Bohr's theory. Let's start from energy of an electron with the help of Bohr's theory. So equation number 1 again recalled, mv square by r equal to z square by 4 pi epsilon 0 r square, and after rearranging we get the relationship mv square equals to z square by 4 pi epsilon 0 r. Now we have to calculate the kinetic energy of an electron, which is nothing but equal to half mv square, and in place of mv square we can put this value z square by 4 pi epsilon 0 r, and we get the value finally z square by 8 pi epsilon 0 r. This is the kinetic energy. And what is the potential energy? The potential energy felt by an electron of charge minus e at distance r from the central charge Ze will be following the Coulomb's law of attraction. So this is q1 into q2 by r. Okay, so q1 is Ze, q2 is minus e, and r is 4 pi epsilon 0 r. Okay, because in there is vacuum, permittivity of a vacuum, you have to input this factor. So the value is minus z square by 4 pi epsilon 0 r according to the Coulomb's law, and the overall total energy is potential energy plus kinetic energy. So this is the summation of these two, and the result is minus z square by 8 pi epsilon 0 r. Okay, now we have equation number 2 where we have the expression of the radius r, and it is the it has the expression n square h square epsilon 0 by pi mz square. This is equation number 2 which was discussed earlier in the previous lecture. Putting this value of r in this equation, so this will go to the denominator and this will go to the numerator, just reversed. Okay, when it is put here in place of this, so in the denominator you can see n square h square epsilon 0, and in the numerator you can see pi mz square, and the other values are same. That means z is square, here z is square, 8 pi epsilon 0 r, here 8 pi epsilon 0. In place of r just we have put this value, okay, and the negative sign carried forwarded, and the final value of E, that means the energy expression. This is minus mz square e to the power 4 by 8 epsilon 0 square n square h square. Now can you say which are the variable terms here? You can easily say only z and n are variable, others are constants. So the proportionality relationship, let me block this first, then the proportionality relationship is E versus z square by n square. This is very important, you have to utilize this. Now let's move on to the next subtopic, which is energy of transition from one level to another level. Energy of an electron in n1 and n2 levels are respectively what? E1, the first n1 level E1 and n2 level E2, and the corresponding expressions only change this value. In place of n you have to write n1 for E1, and in place of n you have to write n2 for E2. All the other things are same. That means mz square e to the 4, 8 pi square, and h square, all these values remaining the same. Okay, so if the electron jumps from n2 level to n1 level, then the energy released should be delta E equals to E2 minus E1, and here only apart from these two other things are same, so you just take them as common. And since there is negative sign, so 1 by n1 square is taken to the left part and 1 by n2 square is taken to the right part. That means they have changed their positions, interchanged their positions. So it is mz square e to the power 4 by 8 epsilon 0 square h square, then into 1 by n1 square minus 1 by n2 square. Okay, now this value of energy is nothing but h nu, and h nu is hc by lambda. Now 1 by lambda is nu bar, isn't it? Because if c is velocity of light and nu is frequency of the light, then you can put nu equals to c by lambda, where lambda is the wavelength of light. Now 1 by lambda is the wave number, nu bar. So instead of E delta E you can write hc nu bar. Okay, and the right hand side is same, or nu bar equals to, just take h and c to the right hand side, so h becomes h cube and c also appearing here in the denominator. other things are same, and finally all these things except z are constant. So take out z square from here, and the rest of the thing m e to the power 4 divided by 8 epsilon 0 square h cube c, these constant terms taken to expressed as only one constant term r, which is known as the Rydberg constant, and this Rydberg constant has the value 1.096776 into 10 to the power 7 meter inverse, and this equation number 5 is known as the Rydberg's equation. And with the help of this Rydberg's equation, we can easily explain the spectra of the hydrogen atom. Okay, and here's the spectral expression of the hydrogen spectra. If the electron jumps to the n1 level from the higher levels, n2, n3, n4, etc., then we will get an ultraviolet light series, which is known as the Lyman series. This way, for n2 level, you get the UV visible in the UV visible range, you will get the Balmer series, and the other rest of the series are Bastian, Brackett, Pfund, and Humphrey. Okay, for n equals to 2, n equals to 3, n equals to 4, n equals to 5, and n equals to 6 respectively. So with the help of the Rydberg equation, just change this value here 1 by 1 square, here 1 by 2 square, 1 by 3 square, 1 by 4 square, 1 by 5 square, 1 by 6 square, and here in place of 1 by n square the value is just 1 extra. That means if it is 1, then it is 2, 3, 4, if it is 2, it is 3, 4, 5, it is 3, and etc., and so on. If it is 6, it is n equals to 7, 8, 9, etc. Okay, so the Bohr's theory provides an explanation of the atomic spectra of hydrogen. The different series of the spectral lines can be obtained by varying the values of n1 and n2 in the Rydberg's equation. Okay, now finally the limitation of the Bohr's theory, what it cannot explain. Number 1, in a Bohr model, the momentum and position of an electron can simultaneously be measured, which is in contrary to the Heisenberg's uncertainty principle. We haven't studied the Heisenberg's uncertainty principle in this lecture series, but we are going to discuss this very soon. But one thing I must say, according to the Heisenberg's uncertainty principle, position and momentum cannot be simultaneously measured together. Okay, so it is in contradiction to the Heisenberg's uncertainty principle. Number 1. Number 2, it fails to explain the intensity of the spectral lines, because one line is very intense, other line is less intense, so it cannot explain that. And it fails to explain the appearances of a set of closely spaced spectral lines observed in the high resolution spectra. You know the Sommerfeld theory, where the suborbit concept would come, and due to that suborbit these lines are actually separated, finely separated, but in the Bohr's theory it is not said here. So these three are the limitations of the Bohr theory. Okay, now move on to the question. The ionization potential of hydrogen atom is 13.6 electron volt. You have to calculate the energy required to remove an electron in the n equals to 2 state of the same atom. Now one thing you must know, that ionization potential is actually the energy of an electron. Okay, they have same magnitude, but the signs are different. Actually the energy of the electron is in the negative sign, so you have to provide some energy provide the electron with some energy. So when the electron is taking up some energy, then this energy is actually ionization potential to dislodge the electron from its position. Okay, so in the energy expression here is the negative sign. Okay, E varies minus z square by n square. Other, if you put a constant term, there is also a negative sign. Okay, but in case of ionization potential, this negative sign becomes positive sign. So for hydrogen atom, for z equals to 1, E varies minus 1 by n square. That means E by n square equals to some constant. That means E1 n1 square equal to E2 n2 square. Okay, so put the value E1 n1 equal to 1 and E1 equals to, it is given. It is actually ionization potential is 13.6, so the energy of the electron should be what? Now minus 13.6 electron volt. Okay, so this way you get the value E2, energy of the second Bohr orbit. It is minus 3.4 electron volt. Okay, and this, therefore if it is negative sign, so the ionization potential should have the positive sign with the same magnitude. So the ionization potential of the second electron should be plus 3.4 electron volt. Okay, so very simple. Next question, question number 10, or the second question of this lecture series. Calculate the energy of the first Bohr orbit in electron volt. So first Bohr orbit, just put the value of n equals to 1, and the other constant as usual. You get the value, it is minus 13.6 electron volt. Okay. Now move on to question number 11. This is the third question of this lecture series and 11th question of this chapter. It is, if the ionization potential of hydrogen atom is 13.6 electron volt, then what is the ionization potential of the helium ion? Okay, so here Z becomes variable now. And one more thing, you must know that ionization and energy of an electron have the same magnitude. Okay, but they have different sign. In the equation from the Bohr's theory, expression of E, you have got the value in the negative sign. So the electron has the energy in the negative sign. So you have to provide the electron with some energy. So electron taking up some energy and then getting dislodged from its position. That means ionization potential, that is. So ionization potential and energy of an electron have same magnitude but opposite signs. In case of energy of an electron, it is negative. In case of ionization potential, it is positive. Now we have the relationship E varies Z square by N square. The minus sign is irrelevant here. Now E n square by Z square equal to constant. Therefore, E1 n1 square by Z1 square equal to E2 n2 square by Z2 square. Okay. Now put the values. Here E1 given energy is, it is plus 13.6 electron volt in terms of ionization potential, so it should be minus 13.6 electron volt. Okay, so here you have to put minus 13.6 electron volt. N1, first Bohr orbit of the hydrogen atom, so it is 1. Z1 for hydrogen atom, it is 1 again. E2, we have to find out this value. Now N2 for the first orbit of helium. This is not the Bohr orbit, it is the orbit of the helium plus ion. So here also the value should be 1. On the other hand, Z2 must be 2 here, because this is helium and its nuclear charge is 2, or atomic number is 2 here. So these values are put here. Minus 13.6, 1 square, 1 square. E2 into 1 square by 2 square. So finally the value of E2 is minus 50.4 electron volt. Therefore, ionization potential would have the same magnitude, but it should be positive. Okay, instead of negative, it should be positive. So the ionization potential of helium plus ion is plus 54.4 electron volt. So that's all for today's lecture. Thank you and have a nice day.